like the title suggests, this is the very first tutorial video on some of the content that we looked at in class. So today, we're going to be looking at the property of exponents. So if you were absent this day, this is a nice chance for you to take a look at what we noticed was always true about exponents. I know some of these formulas look really scary, but essentially, you just need to know one thing, and it comes from a fairly basic idea. So let me show you what that basic idea was. So we started the conversation saying that if we have some number to a power, so for example, if we have something like 3 to the 4th times 3 to the 5th, we said that that was going to be equal to 3 to the 9th. One of the noticings that we saw was that we add the exponents, and so we were pressed to think about why would it make sense that we can just simply add the exponents, because we don't always add the exponent. In this case, it looks like the pattern says that we do. So our justification looked like this. This is a multiplication, and 3 to the 4th lets us know that we are multiplying 3 by itself 4 times. And so we literally just wrote it out, 3 times 3 times 3 times 3. And then it says you are going to times by 5 more 3s. 1, 2, 3, 4, 5, and that is a little 3. And so if you were to see this in the beginning, you would obviously say, well, duh, that is 3 to the 9th. So it turns out that 3 to the 4th times 3 to the 5th is equivalent to multiplying 9 3s together. And we kind of shaded that area here. Here's the 4 3s happening, and then here's the 5 extra 3s. So it's kind of like, duh, yeah. We can add exponents because in total, we have 9 3s being multiplied. 4 of them here, 5 of them there. Then we also notice that, hey, guess what? It doesn't matter that this is a 3. So for example, if it said 7 to the 4th times 7 to the 5th, that would still equal, like the pattern wouldn't change. We would still have 7 to the 9th. Because this is saying the same exact thing. We have 4 7s being multiplied together times 5 more 7s being multiplied together. So in total, we are multiplying 9 7s together. So it doesn't matter what that base number is, as long as it's the same. This base number doesn't matter, but the base number must be the same. Because it wouldn't make sense to say, like for example, this is a bad example, so I'm going to put it in red. This wouldn't make any logical sense. Like if we had 7 to the 4th times 3 to the 5th, we wouldn't say that that's 21 to the 9th. We wouldn't say that, oh, well now there's 9 21s being multiplied together. No, that's not consistent with what we know about exponents. So that is not a thing. Don't worry about it. Forget about it. You're going to throw that in the trash. Doesn't make any sense. So where this took us was extending it and generalizing it to this. We noticed that if you have a number to a power times that same number to a separate power, we simply noticed that, well, that can be condensed because you can add the exponents. In total, you are going to have a plus b amount of a's being multiplied together. A total of a plus b, or sorry, b plus c, a total of b plus c a's being multiplied. This is a property of exponents. It's not a rule. I don't like the term rule. I think that makes it seem like there's all these arbitrary rules. No, it's just a property of exponents. It just so happens that if exponents act like we know, then we know that this is going to be true. So then we can press this, we can stress this, we can manipulate this to check to see how strong, how much do we want this to be true, in other words. We look at this property of exponents and we ask the question, how much do we want this to be true? So let's see what happens with 0 exponents. So how much do we want this to be true? So if we had something like 7 to the 9th times 7 to the 0, if we want this to be true, which it makes a stupid amount of sense, we have a total of a certain number be multiplied together. If we want this to be true, well then what would this have to be? What would 7 to the 9th times 7 to the 0 have to be? Well, if we want this to be true, we're going to add those together. And we're going to say that this is 7 to the 9th. 7 to the 9th is some big number, so I'll just say that. This is a huge number, a big number. So that's a big number, and we are multiplying it by 7 to the 0. And it turns out, if we want this to be true, we're going to get the same exact big number. So we have big number times something equals the same thing. So we have a number times something is the same number. Some of you are probably already guessing where this is going to go. If this is true, if we have a big number times something equals the same big number, what does this have to equal? Big number times 1 is going to be equal to big number. I don't care what that number is. But I know that if we can add exponents, then 7 to the 0 must be 1. If we still want this to be true. And it doesn't matter that it's a 7. It could be a 5. This would still be the same. So a little sidebar here. We know that 5 to the 9th times 5 to the 0 would still have to be 5 to the 9th. We could use the same logic. This has to be a value of 1. It could be 2 squared times 2 to the 0 still equals 2 squared. And you know that 4 times blank d equals 4. You would know how to solve that. That's like basic, you could figure that out. You algebra 2Zs. You know that that has to be 1. If we want to be able to add exponents, which we do, then this is also a property of exponents. It's not a rule. It's just a property of exponents. If this is true, then a number to the 0 is going to be equal to 1, except 0. This is true because we want this to be true. We'll do a separate video on why it wouldn't make sense for a to be 0. But if you're so inclined, feel free to tackle it yourself. Why can't a equal 0 if we want this to be true? End of video.